lag. Okay, so from lecture 3, hopefully what we covered was clear. We talked about estimation. What we didn't go into too much detail was, we didn't expand much on this here. So we notioned the of course he's so fiddly. Okay. So we talked about serial correlation in the go away. So one of the crucial assumptions so we have an ARP model. One of the crucial assumptions for OLS to be unbiased is that the error terms are uncorrelated with the regressors. And we saw how if epsilon t is serially correlated, then it means that epsilon, the shock, is correlated with some epsilon t in the past. So is everyone clear on why serial correlation causes the bias? So for example, if the covariance of epsilon t and epsilon t minus 1 doesn't equal 0, say for example, why this will imply that the error term must be correlated with the regressors. So that's a problem that serial correlation causes, and you just need to understand it at that level, that if the errors are serially correlated, then it means that the errors must be correlated with the regressors, because of course all these lags of y, these are all functions of this is a function of epsilon t minus 1, this is a function of epsilon t minus p, and so on. Okay, so we know when there's serial correlation, there is a bias in OLS. So that's a problem. And another issue is that when the errors are serially correlated, then it means that we've not specified all the dynamics. So, for example, the error terms, for example, may be, say, an AR1. So it may be that the error terms are an AR1, where VT is a white noise, sigma squared. So in this case, so we have a model. We have this model above. The model's in ARP, where the residuals, if they're correlated, they could be an AR1 or an AR2 or an MA1. So this could be one example. This would mean that the errors were correlated just at lag 1. Okay, and we can then we'll give examples of this. We can from here work out what the true model would be. We can just plug in epsilon t into here and epsilon t minus 1, and then rearrange. So if the errors are serially correlated, it means we've missed out some of the dynamics. So if the true errors were serially correlated like this, then it would mean that the true process y would be a more complex model. And we can actually work out what that model would have to be. But firstly, let's talk about how do we test for serial correlation. And you only need to be able to outline the steps of the test. You don't need to be able to prove why it works or so on. So okay. So hopefully you've watched the video clip on this. So we'll run through the, and stop me if you've got any questions. We will run through the Godfrey LM test. Using the case of running an AR1. Everything goes through the same with any model. But let's just say we're running an AR1. So we want to run yt equals mu plus psi1. Okay, and we believe the errors may be correlated. So we want to run a test where the null hypothesis is that epsilon t is serially uncorrelated against the alternative that it is correlated. So we want to do a test which will allow us to test this. What the Godfrey LM test actually does is it tests whether or not the errors are an AR model. So when we come on Tuesday, tomorrow, when we come to do this test, the test will ask you to specify the number of lags you want to include. And what that means is the null hypothesis of the Bruce-Godfrey LM test is that the error terms are an ARK model, where K will be the number of lags. So we might want to test the null hypothesis that the errors are serially correlated against the alternative that it's an ARK process. So again, we'll talk more about this, but this is how we set up the null. We essentially hypothesize that the error terms may be an ARK model. So epsilon t, call it say I don't know, rho 1 epsilon t minus 1. This would mean that the errors terms were an ARK process. So we might have this. The null hypothesis will then be that all of these coefficients are not. So we'll test the null against that at least one of them for some j. This just means that for at least one of them, the coefficient is non-zero. Okay, so the point here is that this null hypothesis is way too broad. Testing that epsilon t is correlated or not, well, there's epsilon t could be correlated with any lag in the past, and there's an infinite number of them. So we have to make a more specific null hypothesis. So the Bruce-Godfrey LM test technically tests the null that we specify that if there was serial correlation, it would be an ARK for some k. For example, we might believe that if there was serial correlation, it would mean the errors were an AR2 or an AR4. So we specify k. Example k equal 4, and then we do the test. So under the null, under the null, if there's no serial correlation, all these coefficients should be not. And if there was some correlation, at least one of them wouldn't be 0. Okay, so hopefully everyone's clear on the idea, the null hypothesis we're testing. And again, you just have to follow the intuition. This is the broader test we're doing. Are they serially correlated or not? And we've actually got to zoom in and give a specific null. So we'll hypothesize. We have to make a hypothesis if there was serial correlation, what kind of form it would be, and then test. Okay, so this is technically what the Bruce-Godfrey LM test will test. It will test that all these coefficients are not. Okay, so if we reject the null hypothesis, then there's evidence the errors would be an ARK where some of these coefficients would be non-zero. Okay, so how do we do this then? So the idea of the test is we want to test whether or not this error term has this ARK form. More generally, we want to test whether the residuals, these shocks, are serially correlated. So in order to do this, we need to be able to measure the shock. We need to be able to estimate this. And of course, we don't observe the shock. We observe y into the past, but we don't observe the shock. So what's going to be the obvious way to estimate epsilon t? How can we work out epsilon t? So under the null hypothesis, there is no serial correlation, which means that OLS will consistently estimate these parameters here. So we run OLS. So how are we going to estimate? What's the intuition here? We estimate. We get mu hat, phi hat 1, and then what do you think we'll do next? With this, what will we do? How will we use this to estimate epsilon t? We run OLS. We realize that under the null hypothesis, because there's no serial correlation, then OLS is consistent. So if a sample size is large enough, these coefficients will be near the true coefficients. So how can we use these estimates and y to estimate epsilon t? Well, what's the intuition here? How would using all this, how would you construct a best guess of epsilon t? Well, we just take the fitted value. We would take, our best guess would be mu hat yt minus mu hat minus phi hat 1 yt minus 1. We call this epsilon hat t. So you realise, you remember this from last year when you did OLS. This is the residual, the estimated residual. So is everyone hearing me all right? No one's written anything for a while. I hope I've not gone off. I'm not sat here talking to myself. Are we still running? The chat's kind of stopped. Is it still going?